Alright, hello guys, welcome to my channel. So in this video we will discuss about linear regression. So regression basically means a real valued outputs, and we can see the linear regression, the definition of linear regression as defined in Wikipedia. It says that a linear regression is a linear modeling excuse me, a linear regression is a linear approach for modeling the relationship between a scalar response and one or more explanatory variables, also known as dependent and independent variables. So it says about a relationship. We'll call that relationship as f. F is a function. Mathematically, a function is nothing but a relationship. So f is a relationship between what? Between a scalar response. Let's say this scalar response is my y. Between a scalar response y that belongs to a real number and x, it belongs to a real number, since if it's one variable. If it's two variables, then it will belong to R2. If it's 69 variables, it will belong to 69. If it's n variables, it will belong to Rn. So what does this imply? This means that there is a function, like given a dataset D in this format, x and y pairs, there is a function f, or a relationship. There is a function that explains the relationship between x and y's of the dataset. So we believe that, so we assume that there exists a function that absolutely explains, that correctly explains the relationship between x and y's of the dataset. And we don't know the function yet. We have no clue what that function is. So our goal is to figure out what that function is. So how are we supposed to do that? Well, we'll see that shortly. So this is our dataset D. It comprises of x and y's. X is the input and x belongs to the real number, like x belongs to Rn. X is n-dimensional vector and y is a simple scalar, just a real number, right? So x can be represented, you can see over here, x is represented as a vector x1t, and this is how the entire dataset looks like this is the entire dataset, vectorized format. So first, this is a one single point. So for this input, x1 input, you will have your corresponding y1 output, the scalar response. Similarly, for xn input, you will have your yn output, scalar response. So we believe that there is a target function which is called f of x. Now our goal is to approximate f of x using h. H is our hypothesis. This is our hypothesis. So in this linear regression problem or task, we have a hypothesis, and that is the summation of w's, which are known as weights. This will be actually I. Yeah, so this will be the summation of x, summation of the multiplication of x, the inputs, and some scaled by some value, which are known as weights or parameters. So linear regression is called linear because it is h of x, it is linear in parameters, means w's, it is linear in w's. It means that, let's say you have some h of x, like w x squared plus w1 x. This function h is also linear in w's. This is also linear in w's, but this is non-linear in x. Right? Had this been like w square and w, then in that case that would have been a polynomial regression. But in our case, since this is linear since we are dealing with linear regression, so the hypothesis function of the hypothesis will be or must be linear in parameters, or the W's, right? So our goal is to find a H hypothesis, find a H from the hypothesis set such that it will approximate F well. Now, how well does H approximates F is known as the error, and that is defined by the square difference between the response given by our hypothesis and the actual response, which is known as the ground truth from the dataset. This is also known as MSE, or the mean square error, and this is for a single sample. So this is for a single sample. Now, if you if you take into consideration the whole dataset, if you take the whole dataset into consideration, then in that case, this will be your entire loss, entire MSE error, right? So you have the hypothesis, and this is your ground truth. You take the square distance, and you take the mean, hence the name mean squared error, right? So this is basically the mean squared error, and this is the equivalent vector form. This is the equivalent vector form. This x is same as this capital X. This W is nothing but a vector, and you can see that there I have given here n plus 1. Why n plus 1? That is because your x will be like, your x is basically, let's say your x1 will start from x10 till x1n. So this will have n cross n plus 1 dimension, and the value of x10 will always be 1, as you can see from here. So basically, why do we do this is to involve a term called bias into the hypothesis. So originally my hypothesis will be W transpose X plus B. Originally my hypothesis will be W transpose X, but we add a bias term to it, and this X has n elements. This W also has n elements, otherwise the dot product between them is not defined. So these two have n elements, and you add a single element, which is B. So and this is basically an affine function. Now if you want to transform this into something like this, W transpose X, then you can do that simply using simply increasing the length of the vector input vector by 1 and assigning 1 to the first value, and then include this B into the weight vector. So that's how you get n plus 1. I hope I was clear. Right, so next thing is these are all fine. Like, we found out the MSE loss, we found out the error, but now how well does it approximate? So this number, the MSE loss you get, the smaller the better, basically. So the smaller than the error, better it is. The smaller the better. That's what she said. So that's it. And next is we need to find the optimal set of weights such that this MSE will be minimized. Such that because if MSE is minimized, that means that function approximates F well. It can actually explain the behavior between the x and y's of the dataset, right? So we will minimize this MSE loss function. And how are we supposed to do that? So any minimization problem, what you do, you find out the derivative with respect to the variable you're trying to minimize with. So in this case, you see in the hypothesis, if you look at the hypothesis, yeah, all the x's are given and all the y's are also given. So what you have at hand, you only have the w's, which you can change. So if you tweak those w's, those are known as degrees of freedom. So if you tweak those w's, you will get a specific value of y hat. We will call it y hat. Now ideally it should give the y, the corresponding ground truths. But how far off your result is from the actual truth, that is the error. And we have to minimize that error. So your variables are weights, you can only change the weight. So you have to differentiate the loss function with respect to weights and equate that to 0. Because let's take a simplest example. So h of x equals wx in it. So h of x equals wx. And now your loss function, like I'll simply give it L equals wx minus y whole square. So if you look at this carefully, then this is nothing but a parabola. The L is of w, so this is w, and this is basically a parabola. Now L, we have to minimize this L, right? So L is minimum at what? L is minimum at this point, which is, this is basically L is 0. At this point L is 0. Now we have to find that particular w where L is 0. We have to find the w prime where L is 0. So we have to find the set of w's, set of weights, such that it will minimize the entire error. So we equate, we find the derivative of the loss function, and we find the derivative of the loss function with respect to weights, and we equate that to 0. And then this is the formula that we get. This is the solution to the equation 1. So this is the simple derivative, you know. So if you look at this equation, I'm just doing, yeah. So if you look at this equation, you have this one. This is your error vectorized format. Now if you differentiate this with respect to weights, then this 2 will come in front, n is a constant, will be there, and then this entire thing will be here, and you get xt because you're differentiating with weight. So this will be treated as a constant, x will be treated as a constant, and it will go outside, hence you get xt over here. This is the next step. We are just splitting the, we're just opening the brackets, and then this is the actual answer you get. This is the value of weight you get. Right, so to minimize this is the solution. You can do that, and also you can get the set of weights, like the proper weights. You can also get the proper combination of weights using the gradient descent algorithm, and I have discussed the gradient descent algorithm in other videos. Please go ahead and check those out. And so here this is known as the normal equation, right? Next are the different matrices of, you know, evaluating a linear regression. So we all know that MAC loss, and this is MAE loss. MAE loss, basically this is an absolute value. So the graph of this MAC loss, this will look something like this, like a parabola, right? And the graph of MAE, this is my MSE, and this is MAE. MAE will look like a mod x, right? So you know the nature of mod x, and mod x, the only problem with the graph of mod x is that in here, at this particular point, it is not differentiable. But in case of MSE, this is differentiable throughout. And root mean square RMSE is nothing but the root over of MSE. And R square, and this is one thing which basically you calculate the MSE, and then you calculate the covariance. Basically you can calculate the variance. So MSE by variance, and you subtract that from 1, and you get a score. So if this score is closer to 1, then that means your model is good. If it's closer to 0, then that means your model, you might wanna go through your notes and improve your model. So that's one thing. Now we'll simply go ahead and take a look at an implementation. So this is an implementation and the dataset. Yeah, so this is our hypothesis. This is basically a curve fitting problem. It will take a bit of time. Right. So this is we have only one x and one y. So we have only one variable, and we have corresponding y value. Clear the shape. We can see there is only one null value, so we'll remove it. We have to remove it, so we can remove that using this drop now, like this drop na, and axis will set to 0 because of we will remove this row itself. So this will remove the entire row, and now you get 699 values. Earlier you had where is it? Yeah, earlier you had 700 values, and this is the row where you can see that y value is nn is not defined, so you need to remove that row. So hence you choose axis as 0. So if you want to remove a row, you choose axis as 0. Now let me just simply describe, and you can see that max value is 100 and 108, and you have 69 values of x and y's. So that's good. Now let us just simply plot the dataset. So this is how it looks like. Nice, quite. And we can know from the dataset that we have to use the hypothesis set, like the hypothesis that we will use has to be linear in nature. Now we'll convert this into NumPy arrays. We'll normalize it. Then we'll add ones to it, because I have already said that in this one. Here you go. Yeah, you have your one, but you add the bias term. Hence, you have to add 1 to the entire input vector. So now your dimension is 699 cross 2. This is the train x. This is your training data set. This is the definition of L2 norm, which is the loss function, MAC loss. This is your gradients, because if you see over here, this is the loss, and if you calculate dl by dw, then you will get this answer. dl by dw, you will get this answer. So 2 comes out. So the derivative of this thing is 2 comes out, and you differentiate the expression in between. Rather the inner expression. So now I have chosen, I have initialized the weight matrix, the weight vector, and then this is the training process. So if I run it, so this was my weight before, and this is the loss at each epoch. Epoch means basically your hypothesis will take into consideration, they will take every data point into consideration, and after training is over, this is your ultimate loss. Now if I plot this, so you see that the blue line over here, where is it? Yeah, this is blue line. So blue line was my previous regression. With my blue line was my previous weight, basically the regression line with these weights, weights before training. And this red line, you can see this is the regression line after training with these weights. Right. So as you can clearly see, it has done a quite good job, in approximating the target function, which is f of x, which I believe to be a straight line like this. some sort. Now next is we have to like do this on the test set, so let's go ahead and do it. So this is how it performs on the test set, which is pretty good, I believe. It's not that bad. Yeah, this is good, pretty good. Now next comes the normal equation. I have told you that this is the normal equation. This is the solution to the linear equation, like this, sorry, linear regression. This is this one, this is equation. This is the implementation of the same, right? And you can see you can calculate you will get the weights at one shot just by implementing this normal equation, right? So this is the ultimate weight that will reduce the loss. So this is basically, this is the loss. So we considered the weights given by this method, this gradient descent method, right? And this is the weight, this is the loss, this is the loss after getting the weights from gradient descent method, and this is the loss after getting weights from normal equation, using normal equation. Now if you plot both the graph, so you can see that the normal equation and SDE, they actually lined up quite well, you know. So if you see the weights, then you can see that they're almost close to each other, right? These weights from gradient descent, we got these weights from using gradient descent, and this we got it using the normal equation. So you can see that these two weights are pretty similar, right? So that's it. That was all about linear regression. I hope I was clear. I was able to explain the basics of linear regression. Right. All right then. Thanks for watching. Adios. And let me know in the comment section like how was this explanation. Like what parts should I improve? You know. Thank you.